I'm founder of Percepio, and as mentioned, the title of my talk today is Visual Trace Diagnostics on Zephyr applications. This is about 20 minutes of content, so there should be some time to take questions afterwards. My focus over the last years has been about visual trace diagnostics, and I will explain what I mean by that. But the purpose is to simplify embedded software development. I'm the original developer of our tool Percepio Tracealyzer, but today I'm mostly focused on running the company. I have 20 years experience in RTOS and RTOS tracing, 2 granted patents, a PhD in computer science, and that project was basically about practical methods for embedded system timing analysis, performed in collaboration with regional industry. And I spent my initial career at ABB Robotics doing software development for motion control and industrial robots. You may have noticed in Zephyr 2.6 there is some new options for tracing. If you look under subsystems and OS services and tracing support, you can now find Percepio Tracealyzer. By selecting this option, you include our trace recorder library that has now been adapted for Zephyr and is provided under Apache 2.0. The code is found under modules, debug, trace recorder. The purpose of this recorder library is to provide data for what we call visual trace diagnostics using Percepio Tracealyzer. And this is mainly targeting application developers, I should say, perhaps not as much kernel development, although there are probably cases for that too. If we look at the big picture here, this trace recorder, I like to think that this sits in between the RTOS kernel and the embedded application, because it provides, well, the trace recorder is used by both. It records kernel activity, and you can also make explicit calls to the recorder from the application code to log additional events. The data is then transferred over to a host PC and the Tracealizer host application that visualizes the data. Here is a snapshot, a screenshot of Tracealizer, giving a glimpse of what this tool can show and what we can do with it. It supports live trace streaming, and one thing that is pretty unique with Tracealizer is that it allows for the streaming is flexible, so you can use basically any target to host channel that you may have available. We have stream ports, as we call them, prepared already for ITM SWO on ST-Link, for instance, on STM32 devices, and for Sega J-Link with RTT. But you can also use functional I/O for streaming trace data like Wi-Fi or a TCP socket or a USB CDC or something like that. You can have a look in the stream ports folder, and there's a header file in different versions called trc streamingport.h, where you can define how to output the data. This tool has been developed since 2009, and this is a commercial product, so you actually have to pay for it. The host application is not open source, only the target side recorder. But we have a generous offer for academic users, completely free of charge, like that. It's available for several different RTOSes, now also Zephyr, as well as Linux using LTTNG. And on the host side, we support Windows and Linux. So I mentioned this term visual trace diagnostics a couple of times. What do we mean by that? And how is that different from software tracing in general? Well, software tracing is the base, the foundation, that's the input. A software trace is a list of software events, and that can mean anything really, but typically you have a timestamp, typically detailed microseconds or better. You have an event code, for instance, like 42, meaning say a context switch, and then you have some event-specific arguments for a context switch event that could, for instance, specify that the thread that is about to start is my thread, for instance. So if you record this kind of information and output it to a text file, then you can get something like this. And this can be really useful for verifying specific things when you know what you're looking for, what happens at point X in my system. But it can be quite challenging to use a text log like this for debugging purposes. When you're logging kernel activity and certain application activity, you get a lot of data, and that can be quite difficult to overview. And in a text log like this, also, you don't really have a sense of the elapsed time. You can see the time here, but it's difficult to see that this is close and this is far apart, for instance. But especially when you're doing debugging, and especially on system level, you're not always sure what to search for. You're not always sure. You don't always know what you're looking for. Maybe you have a symptom on a high level, perhaps an error message in a terminal, or you see a glitch somehow in the system behavior. But it's difficult to know how that will appear in the trace view. So to address this, we have a second step where we process this event data into what we call an object graph. And we use a semantic model of the events. By this, we mean that we have an XML file basically with annotations that describe both the arguments of these events and what the events actually mean. For instance, if we are logging mutex events, as this example describes, this is part of our model for the Zephyr kernel. Then we understand that mutex events all have a handle that identify a mutex object. Tracealizer will then create a mutex object in the internal model. And this a mutex object is understood to have an owner, kind of a state, that identifies a particular thread. And we also understand that a mutex has a lock and an unlock operation that can be used by different threads to access a shared resource. And we have similar models for all sorts of objects, and so it's a kind of an extended awareness from the tool side. And when you create a data model with this kind of insight into the trace, this kind of understanding, you get this fairly rich model that can be visualized from many perspectives and at different abstraction levels. And the point of this is that you can have multiple connected views that allow for a top-down workflow that is very suitable for debugging. You can see anomalies visually in overviews and then drill down to analyze the cause. There's an example here where we have a plot of thread response times. Basically, the time from a task or a thread is activated until it goes back to sleep. And in most cases, this is really short, but here we have a case where it's 80 milliseconds. And if you're curious why that's the case, you can click on this and see and let the tool show a more detailed trace view here of that particular point. So use cases. I mean, this is nice and all, of course, and we all want diagnostics in various forms, but I've been thinking a lot about this, how in what situations you can really benefit from having this kind of analysis. And what I came up with are basically three areas. One is debugging of multi-threaded RTOS applications, especially when you have issues related to multithreading, like semaphores, mutexes, scheduling. When you have issues related to resource usage, like timing, CPU load, etc., or software timing, if you have a particular requirement that something need to execute within a certain time. But also when you have a case where the target system can't be halted for traditional debugging, maybe you have a communication protocol with some real-time requirement. That means that if you halt the device, then things will time out and you'll basically break the system and you can't continue debugging. Or in general, whenever you want a timeline of the software, this can be really handy in many different situations, especially to see that things are executing the way you think it is. It can also be used to analyze application design, and I mean that in a pretty broad sense. One thing is that you can analyze functional behavior over time, for instance, plotting application data variables in your code or as state diagrams. But you can do that together with the overall system level execution of threads and kernel objects. And that's really handy for kind of getting a sense that the system is actually working the way you designed it to be, or if there are some weird issues going on that you want to investigate. Another thing is to detect kind of violations with respect to best practices. I mean, designing multi-threaded software systems is a really tricky business, and there are many pitfalls. But there are also a lot of wisdom in the industry on how to do it right, kind of best practices. I don't know if anyone have formalized this, but I mean, in general, for instance, you should try to avoid using busy waiting instead suspend tasks to allow other tasks to execute. You should avoid having a lot of variability in timing because that affects testability, etc. So, I mean, there are lots of things you can check for. And third, by measuring in runtime, a very low-hanging fruit is to measure software timing, resource utilization, and software performance, not only to get the numbers, but to see the reason behind the numbers, so you can find the bottlenecks and optimize. And I mean, this way you can improve the application performance and user experience, but you can also say that you managed to reduce the CPU usage a lot. Then you can perhaps settle for a smaller processor in your product and reduce the bill of materials. And that can be a quite important saving. In general, it's often possible to get pretty big improvements in performance with small changes if you have the insights, so you know what to change, basically. I mean, you can spend many hours on blind optimizations in the code, but if that's not really the bottleneck, then you're basically wasting your time. If you're finding the exactly the right thing to optimize that really matters, then changing a single line of code can have huge can make a big difference. So now I'm going to show you a couple of screenshots from Tracealizer on giving examples of things you can see, and also some examples of how you can use the recorder library to log additional information. By default, you can get kind of some events are traced automatically from the existing tracing hooks in the kernel combined with the trace recorder library. We get things like context switches, tasks, and API calls, and certain other kernel events. And this can look something like this. On the left, we see a vertical timeline over the thread scheduling. The different colors show actually thread priority. Red means very important, urgent, while blue is less important, for instance. And on the right side, we have a list of floating labels that they kind of adapt and spread out as needed, showing the different API calls that have been made during these in these threads. And you can see that some of them are green. There's a red one in the middle that indicates the status of the operation, if there is blocking or if it's a resume from a blocking call. And there are also orange labels for timeouts, etc. The very same information can also be shown from in different ways. Like here we have basically taken the scheduling events and shown that as a CPU load graph, where we see the distribution of CPU time, basically what threads are using most of the processor time during different periods. So the x-axis is here the timeline, and we can see peaks where we have activity. This system is fairly idle normally, but about once a second we have a burst of activity. If we like to, we can double click on one of these peaks and see more in detail in the trace view what's going on there. This view is quite interesting, I think. It's called the communication flow. It basically shows the inter-process communication or inter-thread communication in runtime. It's basically a summary of the API tracing. So each API call, for instance, calling accessing a mutex, is like a relation between a thread and this object, this mutex. And if treating this as a graph, then this is what you get. So this is kind of a architectural feedback from the runtime system that allows you to verify that the system behaves the way you think it is, and you can see if there are any unexpected dependencies or excessive dependencies, and that's great to know for optimizing the system. This view is also interactive, so you can click on particular nodes here in the graph and see all events that have referred to that object, basically all such events. So here we have all the operations made on this FIFO queue, for instance. And if you click in this list, then it's shown in the main trace view, so you get the full context and see other tasks together with this. You can also get high-level statistics on timing, things like execution time, that's the net time used by a thread, and response time, that's the time from it's activated until it goes back to sleep, basically. So sometimes we can see interesting deviations here. In this case, we have the execution time is at most 916 microseconds, but the response time, the gross execution time, so to say, from start to completion is about 1,000 times larger, about 100 milliseconds. And the minimum and maximum values here, they refer to the minimum and maximum observed, not the theoretical maximums, but they are links to the particular instances. So if you click here, then we can find this particular case. We see this yellow task is actually shaded, and that means it's not executing, but there's a small solid block in the end here where it's executing. So it's actually blocked by a mutex or something. And we have a lot of other overviews, for instance, this plot over response times. But you can also see other things like stack and heap usage and things like that. If you add some additional code in your application or maybe an interrupt or so, you can log basically whatever you like. Here we have a demo application that is using Bluetooth BLE, and it's logging the signal strength to nearby devices. So this function here, vtraceprintf, that's part of our recorder library, and it's used in a similar way to printf. Not all the format string options are supported, but many. And the first parameter here is a name, a channel name for this user event. So in this case, we're using the BLE device ID. This is just a string, it's not individual numbers. So this part is the channel name, and here is the value we're logging formatted as a signed integer, like this. And if we when we're logging data explicitly like this, then the Tracealizer is aware of this as an integer and can plot it as well. So we can have time series like this and see how inputs and outputs and how internal algorithms behave over time. And if you're interested in a particular point, you can click on it and see it where it's logged at the particular point in the trace. You can also log strings and names to, for instance, to add additional debug information in your application. Here we are logging state changes in the Bluetooth stack. So we have 3 states, scanning, connected, and disconnected. And this column here, these 3 swim lanes, are not tasks or threads, but they are what we call intervals. They are kind of a made up representation of the time between 2 events. So this red interval here is the time from connected until disconnecting. So we have a couple of other vtrace print calls at other locations in the code that are logging these other states. And these intervals can be plotted as well, so we see their durations like this. So here we see that the duration was about 250 milliseconds, which is pretty high. In other cases, it's around 50 or 100 milliseconds. And intervals can be used for basically any kind of systematic measurements. As long as you have an event, you can define an interval between those events and see it like this. In this case, states are actually a special kind of interval because the states also have a state, a value, and we can show state diagrams like this. If you're logging general intervals, the time from A to B, then that's not really a state. But if we make Tracealizer aware of this as a state machine and say how to read this, basically say that this is a state, then it will present something like this, and you can compare with your design. So how do you enable Tracealizer support in Zephyr then? The first step is to enable tracing in general. Under subsystems and OS services, tracing support, you find this where you can define or enable different enable tracing of different kinds of events, and this is a good way to filter the trace. If you enable too much, then perhaps you get more data than your data channel can handle. So sometimes you may need to reduce the tracing to be able to cope with the data rate. And then you select Percepio Tracealyzer, and then we also have this option for the Percepio Trace Recorder, where here's again with some explanation is here. The first one is currently just streaming. It's not much to choose from there. In general, we have another mode called snapshot mode, where the trace is recorded to a ring buffer in RAM. And that's currently not supported yet for Zephyr, but it's coming that soon. Then you can select the recorder start mode, and that's basically start means to start tracing directly on startup as soon as the recorder is initialized. If you're using that, then you need to have a Tracealizer ready to start capturing the data right away. Otherwise, you will lose the initial part. The middle option, start await host, will block in the startup until the start command is sent from Tracealizer. That can be nice if you want to make sure you capture everything from the very beginning. Otherwise, you can select initialize, and the recorder library will then be ready to run and start whenever you press the start button in Tracealizer.
Johan, heads up, you've got about 5 minutes left.
Okay, yeah, I'm almost ready. I think I'm taking a bit longer than when I rehearsed this. You have the stack monitor, so you can check periodic stack usage, and you can select the stream port for how to output the data. So to learn more, visit percepio.com or contact us at support@percepio.com. To use Tracealizer on Zephyr, you need Zephyr 2.6, as mentioned, and you need the upcoming Tracealizer 4.5 that is not released yet. This introduces beta level support for Zephyr. It's coming out next week. And you need a way to transfer the data to host, like you use Segger J-Link or something. Okay, sorry for overrunning a bit. Thanks for having me and for joining this presentation. Now it's time for your questions.
So beside, there's a question there.
I have a question in the chat here. This looks very similar to Segger system view. Are there significant differences between the two or their support in Zephyr? This has, in general, Tracealizer is a far more sophisticated tool than system view, even though I'm kind of biased in this, but we have extended the trace support in the Zephyr kernel a lot to be able to take full advantage of the Tracealizer functionality. So yeah, the answer is yes, there is a big difference. There is a reason we're charging for it, and there is a lot of functionality there that people are appreciating. We actually have quite a few customers that have been using Segger system view in the past and have not now become paying customers because they see the value in it. Are the trace hooks SMP aware? I'm actually not sure about how that looks for Zephyr. In general, we have recently added SMP tracing for RTOS, for instance, for the ESP32 version of RTOS. So I know that we can support it in general, but I don't think we have it in Zephyr yet, but that's coming. Yeah, there was another question about multicore. Yes, that's coming. What about other architecture other than ARM? Yeah, we Tracealizer or the trace recorder library is not very dependent on the processor. Basically, what we need is a way to toggle interrupts in case we need to do something sensitive, and we need a way to read an accurate time source, like a cycle counter or something like that. So we have support for a handful of families, I believe. Apart from ARM, we have support for some PowerPC processors and PIC32 and yeah, ESP32 is the latest one we've added. Also Neos 2 from Altera. So yeah, it's there are a couple of variants. It's only a handful of macros that needs to be updated, basically. What are the runtime impact of the tracing for analyzing very time-sensitive things? Yes, there can be one. Software tracing has a fundamental challenge with respect to overhead. We are using a few CPU cycles here and there to log things, and we're using a bit of RAM, etc. In some cases, if you have a very tight real-time loop and microseconds really matter, then this might not be the best solution for you. Then you might need something like a Lauterbach or Segger J-Trace or something like that for hardware tracing. But most people that we have, I would say that maybe 1 in 100 of the people I've been in contact with that have evaluated Tracealizer have found the overhead to be a problem. It's typically measured in microseconds per event, that is, and you have typically a few thousand events per second. So the overall CPU load translates into like a 1% overhead or something like that, but it varies a lot depending on the application and the processor speed. Any plans to provide a light version for open source non-commercial use similar to SeggerView? No, we don't have any plans like that. We have tried that in the past, and it basically didn't work. I perfectly understand that people would like that, but we did that 5 years ago or so with the hopes of increasing the organic spread, but we didn't really see that effect.
So Johan, I'm afraid we're out of time. Thank you so much for your presentation. This was really interesting. I look forward to playing with it myself. I'd encourage folks, we do have a Slack channel set up. So if you guys want to continue the conversation, you can jump over onto Slack on the user ecosystem track channel. And with that, thank you everyone for attending. Thanks again, Johan, and talk to you later. Enjoy the rest of your day.
Thank you. Bye-bye.